Welcome to the Deep Dive. We're here to crack open the sources, pull out the crucial insights, and get you up to speed fast. Today, we are tackling a big one in physics, the true nature of light. We're moving past light as just simple rays. We're going to show pretty definitively, I think, that light is a wave. And, well, a surprisingly complex one. Now, guiding us through this, we've had an absolutely fantastic set of sources on wave optics, how light bends, how it overlaps, how it gets filtered. So a huge thank you to the curator, Fizik Özretmeni Hashi Veli for putting together such clear, really insightful material. It's been a great guide.
Absolutely. And our mission today is really to distill that key evidence, the experiments that built this undeniable case for light being a wave. We'll follow the investigation sort of chronologically, focusing on three core things: how light travels, how waves interfere, and what type of wave it actually is. And these aren't just abstract ideas. They have real consequences. They define how well microscopes can see, even the tech behind 3D movies.
Okay, so let's start right at the beginning. Before we can even talk about light bending or interfering, we need to understand how a wave actually moves, propagates. So let's unpack that with Christian Huygens. Where do we start?
Right, Huygens Principle. It's actually quite old, but still incredibly powerful for visualizing how waves move. It avoids all the complex math and just says this: every single point on an existing wavefront, think of it as instantly creating its own tiny new spherical wave, a wavelet.
Ah, okay, so like countless little pebbles dropping in water all along the wave's edge.
Exactly like that. It's this constant ripple effect. The original wave triggers millions of these wavelets.
And the edge, the boundary that touches all those new little spheres that becomes the new wavefront moving forward.
That's precisely it.
Yeah.
And, the beauty of this isn't just that it's a neat idea. It works. It was one of the first models that could actually predict basic optical stuff. By assuming light acted like these wavelets, Huygens could accurately show how light reflects off surfaces, how it bends, refracts when going into water, for example.
Right, the basic rules we learn early on: reflection and refraction.
It showed those behaviors were perfectly consistent with light being a wave.
And if you're finding this a bit abstract, maybe picture waves in a ripple tank, like in a science class. You can actually see those straight wavefronts moving and imagine them being built up from tiny points pushing the next bit of wave forward. It helps visualize it, I think.
It does. It grounds the concept nicely.
Okay, so Huygens gives us the how it moves. But here's where it gets really interesting, doesn't it? Because that model leads directly to the first big proof that light isn't just particles. Diffraction. The bending.
Diffraction, yes. Simply put, it's the fact that waves don't always travel in perfectly straight lines. When they hit an edge or squeeze through a small gap, they bend, they spread out. And the crucial thing here, this really comes through in the sources, is how much they bend. It all depends on a ratio: the wavelength of the light compared to the size of the obstacle or the opening it's passing through.
Okay, so I think most people picture holding something up to a light and getting a nice sharp shadow. But that's not always true.
Not always, no. That sharp shadow happens when the object is, well, huge compared to the light's wavelength. Visible light has tiny wavelengths, so everyday objects cast sharp shadows. But if the opening or the obstacle gets really small, closer in size to the actual wavelength, then the waves bend significantly as they go past the edges, and suddenly that sharp shadow, it's fuzzy, blurred out.
Right. That sounds theoretical, but the example with radio waves makes it so clear. It's very tangible then.
Oh, absolutely. Think about AM versus FM radio. AM signals use these enormous wavelengths, right? Sometimes hundreds of meters long.
Oh, huge.
Compared to that, even a big building or a hill is relatively small. So the AM waves diffract easily. They just bend right around those obstacles. You get reception pretty much everywhere.
But FM radio waves are much shorter, only a few meters, you said. Like 2 to 4 meters?
Exactly. Much, much shorter.
Yeah.
So relative to a big building, those FM wavelengths are small. They act more like visible light in that sense. They cast sharper radio shadows. That's why your FM signal cuts out when you drive behind a big hill or into an underground parking garage. No bending around the corner.
Wow. So diffraction isn't just a weird light thing. It dictates radio coverage.
And it sets hard limits on technology, too. It's the fundamental reason optical microscopes can't just magnify forever. There's a limit to what you can resolve.
Resolution wall, yeah.
Pretty much.
Yeah.
You can only clearly distinguish features down to a size roughly comparable to the wavelength of light you're using. Any smaller than that. And the light waves bend so much around those tiny details that the image just blurs out. You can't see the separation.
So wave optics fundamentally limits our view of the very small. That's a huge takeaway. Okay, so we've got movement, we've got bending. What about waves meeting each other? We need to talk about superposition, what happens when waves overlap, which brings us to interference.
Right, interference. When two waves are in the same place at the same time, their effects just add up. Yeah. The resulting wave is the sum of the individual waves. And this leads to two basic outcomes: constructive and destructive interference.
Okay.
Constructive is when peaks line up with peaks, or troughs line up with troughs. They reinforce each other. Bigger amplitude, stronger wave.
Brighter light in the case of light waves.
Brighter light, exactly. Destructive interference is the opposite. A peak meets a trough. They cancel each other out. Lower amplitude, maybe even zero.
Dimmer light, or even darkness.
Or darkness, yes.
And this whole idea was absolutely critical for the history, wasn't it? Thomas Young's double slit experiment back in 1801, because if light was just particles, like tiny cannonballs, shooting them through two slits should just give you two bright spots on the screen behind. Simple.
Right, two lines corresponding to the two slits. But that is not what Young saw. Not at all. He saw this amazing pattern of alternating bright and dark bands. Fringes, they're called.
The interference pattern.
Exactly. The bright bands, the bright fringes, were where light waves spreading out from the two slits arrived in sync peaks, meeting peaks, constructive interference. The dark fringes were where they arrived out of sync peaks, meeting troughs, canceling each other out. Destructive interference.
And the kicker wasn't just seeing the pattern, it was measuring it, right?
That was the genius of it. By carefully measuring the spacing between those bright and dark fringes, and knowing the distance to the screen and the separation of the slits, Young could actually calculate the wavelengths of different colors of light for the first time ever.
Wow, so it wasn't just philosophical anymore, it was math. Measurable proof.
It was concrete evidence that light, at least under these conditions, behaved exactly like a wave. A huge moment.
Okay, let's take that idea waves canceling and reinforcing and look at color. Because you, listening right now, you've definitely seen this. Ever notice those shimmering, shifting rainbow colors on a soap bubble? Or on like an oil slick on a wet road?
That's it. That's thin film interference. It's a really beautiful, everyday example of wave mechanics in action. It happens when light interacts with a very, very thin layer of material, the film, like the soap film or the oil layer.
So what's happening there? Why the colors? You need two reflections.
You do. That's key. You need two waves to interfere.
Yeah.
So light hits the top surface of the thin film. Some reflects right away.
Okay, ray number one.
Ray number one. The rest of the light goes into the film, travels through it, hits the bottom surface, and reflects off that. Then it comes back out of the film.
Ray number two.
Yeah.
And it meets up with ray number one.
Exactly. But ray number two has traveled an extra distance, right? Yeah. Down and back up through the film. So the two rays, when they recombine and head towards your eye, have traveled slightly different path lengths.
Ah, so they might be out of sync now, like in the double slit experiment.
Precisely. And depending on the exact thickness of the film and the angle you're looking at it from, certain wavelengths of the original white light will interfere constructively, making that color appear bright.
And other wavelengths will interfere destructively, canceling out, making them disappear from the reflection.
Right. And there's another twist. Sometimes, when light reflects off a surface, its phase gets flipped, like a peak becomes a trough instantly. This happens at one of the surfaces in thin films, adding another factor to the interference calculation.
So the color we see isn't paint or pigment, it's literally the structure, the thickness of the film selecting which light waves survive and which get canceled.
That's exactly it. A soap bubble's thickness changes constantly as it swirls and thins. That's why you see that dynamic flowing rainbow of colors. Different thicknesses reinforce different wavelengths.
Amazing. Okay, so propagation, bending, overlapping, interference. We've built a strong case for waves. But now the big question, if light is a wave, what kind of wave is it? This brings us to the final piece of evidence, right? Polarization.
Yes, polarization. This is what proves light isn't just any wave, it's a transverse wave. Transverse means the oscillations, the vibrations of the wave, are perpendicular at right angles to the direction the wave itself is traveling.
Like shaking a rope up and down. The wave travels along the rope horizontally, but the rope itself moves vertically.
Perfect analogy. Now compare that to, say, a sound wave, which is longitudinal.
Right. Sound compresses and expands the air in the same direction it's traveling, like a slinky.
Exactly. Now, unpolarized light, like the light from the sun or a regular light bulb, is vibrating in all possible directions perpendicular to its path. Up, down, left, right, diagonally, everything all mixed together.
A random jumble of transverse vibration.
Polarized light, on the other hand, has had its vibrations restricted, filtered down to just one single plane.
Okay, but how does filtering it prove it's transverse? Why can't we polarize sound?
Ah, that's the crucial point. Think about the sound wave, the longitudinal wave. It's vibrating along the direction of travel. There's no sideways component to filter out. You can't block its vibration based on direction because its vibration is its direction.
I see. There's only one direction of vibration possible.
Right. The very fact that we can filter light's vibrations, that we can select just the vertical ones or just the horizontal ones, proves that those different directional vibrations must exist in the first place, which means it has to be transverse.
Makes sense. And we do this filtering with special materials, like Polaroid filters.
Yes, things like certain crystals, or more commonly, Polaroid filters. These filters are made with long chain molecules all lined up in parallel. Think of it like a microscopic picket fence. Only the light waves vibrating parallel to the pickets can get through. Any light vibrating perpendicular to them gets absorbed or blocked.
Which takes us right back to a really common application, sunglasses. Glare off flat surfaces like water, or a wet road, or snow. That glare is mostly horizontally polarized light.
It is. The reflection process naturally filters it that way. So polarized sunglasses have their picket fence filter aligned vertically.
Ah, so they block the horizontal glare.
Exactly. They block that intense, horizontally vibrating glare, but let the rest of the vertically polarized and unpolarized light through. It cuts the glare dramatically without making everything else too dark. Really clever.
Brilliant. Okay, finally, let's wrap up with maybe the ultimate application of all these wave properties, especially interference, holography.
Yes, holography. It really leverages everything we've discussed to capture something amazing. A true three-dimensional image.
Not like 3D movies, which are kind of a trick, right?
Well, 3D movies use polarization, actually. They send slightly different polarized images to each eye to simulate depth. But holography is different. Traditional photography just records the intensity of the light, the amplitude of the waves. That's why photos are flat. They only capture brightness.
But holograms capture more than just brightness.
They capture the phase of the light waves as well. The phase contains information about the light's direction and its precise position in space when it was recorded. It tells you about the wave's timing and depth.
How do they even record phase?
It requires coherent light, where all the waves are perfectly in sync, which usually means using a laser. You split the laser beam. One part, the object beam, shines on the object and reflects off it. The other part, the reference beam, goes directly to the recording plate. Where the reflected light from the object meets the reference beam, they interfere. They create this incredibly complex, microscopic pattern of constructive and destructive interference fringes on the plate.
So the hologram itself isn't the image, it's a recording of the interference pattern.
Precisely. That pattern encodes all the amplitude and phase information, the full 3D structure of the light waves that came from the object. Then when you illuminate that recorded pattern later with the right kind of light, it diffracts the light in such a way that it reconstructs the original wavefronts.
It rebuilds the light as if the object were still there.
Exactly. Your eyes see the light coming from different angles just as they would from the real object, creating a true three-dimensional image that seems to float in space. It's quite remarkable.
It really is. What an incredible journey then, from just understanding how waves move with Huygens, to seeing how they bend with diffraction, overlap with interference, discovering their transverse nature through polarization, all leading up to capturing 3D reality itself with holography.
It's a fantastic demonstration of how these fundamental wave properties build upon each other, leading to profound understanding and powerful technologies. And again, the source materials from Physik Öğretmeni Hachi Avila Torun were excellent in laying out these connections and applications so clearly.
Absolutely. Clear and detailed. Okay, to wrap up, let's leave you with a final thought to chew on, building on that idea of diffraction. We know our vision's sharpness, the resolution of everything we see, is ultimately limited by the wavelength of visible light. So consider this. What if humans had evolved to see light with much, much longer wavelengths, say in the microwave part of the spectrum, like AM radio waves almost? How would your everyday perception of the world change? Think about the edges of objects, the shadows, the details. What would look sharp? What would look blurry? Something to ponder until our next deep dive.